So our topic today is on sliding contact bearings. Sliding contact bearings. Now, we will later on also talk about rolling contact bearings. You will see that the nature, the behavior of these bearings is different from the other type. So we'll analyze this, then later on, at another stage, we'll talk about the other types. Now, here, first of all, what is a bearing? When you talk about a bearing, you're talking about a member which is supposed to or has the function of supporting another member in motion, thereby allowing some relative motion between the contact surfaces. Of course, it should be carrying a load. Like in most cases, we're talking about a journal, which could be what we call a journal in this case is that central component, the shaft. Then where it is fixed, the inner race of the bearing could be yet another part which is rotating. So what you do with the bearing is to ensure that a member can rotate while still accommodated in some fixed housing, or even two members that are rotating, but you separate them with the use of a bearing so that there is no interference. Classification of bearings, this is where we say the main types of bearings that we have. They usually talk about the nature of the load being supported. So you may have radial or thrust bearings, because these could be those bearings which could be handling radial loads or thrust loads. Also, we talk about them being classified in terms of the nature of contact. So for example, you can have sliding contact bearings, you can have rolling contact bearings, and with the rolling contact bearings, you can also further go to other categories that will help us to define or identify them further. So in this one, we will focus on sliding contact bearings. So this one, we're talking about a sliding action between the load and the bearing. And therefore, those loads being carried, at least we're able to push on and ensure that push on some friction that may happen. But at the same time, what is critical is to ensure that the load is transmitted and disturbed. Now, we talk about some factors like bearings that are lubricated hydrodynamically. So here we're talking, these are bearings that could be rotating or running. So what do we have? What do we need to have? They're supposed to be lubricated well. And you could be surprised that this time around we start talking about lubricants, which should appear in fluid mechanics. Deliberately, these lubricants are supposed to carry away the heat. So that's why we can now go ahead and talk about the hydrodynamic lubrication that should take place, and hence important assumptions that should follow the same. We're talking about the lubricant that is going to be used. It should be one that obeys Newton's law of viscosity. The pressure also is assumed to be constant throughout the fume thickness, meaning unless the fume which is lubricating is disturbed, that thickness perhaps is tampered with. But as long as the thickness is maintained, the pressure is considered to be constant. Even the viscosity, it's assumed to be constant. Though we know in practice that when these lubricants are working, when the bearing is working, the life is wearing out, it is consuming some life. The quality of the lube also normally goes down, but we assume that it remains the same. Then also that the lubricant is incompressible, the flow is one dimensional, not two dimensions, or several. What about the lubricants? What properties are they supposed to have? The lubricants should have viscosity. Of course, we know this is supposed to be the internal resistance to flow. They should have the oiliness. So this is boundary conditions that would help us to prevent friction. Density. Here, you will notice that selection of a lubricant will strictly follow the density, whereby it shouldn't be too dense or less dense, but just according to what the lubricating conditions will require. Then we're talking about viscosity index, the flash point, all these, the properties that a lube should have. This is the lubricant being used for our lubrication of the bearing. Remembering very well that this lubricant is not just there to temper with the friction and reduce it, but also it's there to clean and also carry away the heat, conduct away the heat. So in the calculations that we will do later, that we do even on these bearings, you notice that we're looking at how much heat has been generated in this bearing. How are we getting rid of this heat? Then we later on see whether the bearing will be overheating and how much cooling we'll need. We also have what is known as the bearing characteristic number. The bearing characteristic number. So with this one, we're talking about a fully lubricated bearing. The factors dependent on, there are three: the Zn over P, D over C, then L over D. And here is where now we talk about coefficient of friction. The coefficient of friction is supposed to be equal to, first of all, we have phi, then inside the brackets, either of these. So what is mu? This mu is our coefficient of friction. Then phi, this is just a constant, which talks about a functional relationship. Z is the absolute viscosity of the loop, kg meter per second. Then the P you see there, that's the bearing pressure, Newton per square millimeters. Then D, that's the diameter of the journal or the diameter of the shaft which is being supported. Remember that is where the bearing is installed. L is the length of the bearing. C, the diameter of the clearance. So we see where C has been used, that's actually the clearance diameter. So then the factor Zn over P, that is the one we're talking about as our bearing characteristic number. Dimensionless number, meaning when we use it, no dimensions involved there. That's why it's appropriate that we're using it when we're calculating the coefficient of friction. Then generally, in the journal, what coefficient of friction do we talk about? So here we have coefficient of friction for a journal bearing, 33 over 10 power 8, then Cn over P multiplied by D over C plus the K. Now K, this is a factor to correct for end leakage. These other factors like Z, N, P, these are the ones we already discussed. The only newcomer is K. Critical pressure on journal bearings. So this is where the pressure at which the oil film breaks down so that the metal contact begins. In other words, if you reach the critical pressure, then your member will start overheating because friction will go up very sharply because that lubricating film has been compromised, it has broken down. So to find P, the formula we use, P is Zn over 4.76 by 10 power 6, then D over C squared. Then in the brackets again, L, D plus L. These are not special factors. That's the same ones we talked about. D, diameter of the journal or diameter of that rotating member. C, the diameter of clearance. L, the length of the bearing. And P is the critical pressure. Then we also have what is known as Sommerfeld number, another dimensionless parameter. In the design of journal bearings, this one is also critical. So Sommerfeld number is given by Zn over P, then multiplied by D over C squared, brackets. Like we had mentioned, when a bearing is is working, is operating, you expect heat to be generated. Because of that relative motion between the housing and the rotating member, or between the bearing and the journal, you expect heat to be generated. So heat generated, this is Qg is equal to coefficient of friction multiplied by the load multiplied by the speed at which that member is rotating. So this is coefficient of friction, this is the load, and this is the velocity. Velocity, of course, it has to be in meters per second, but there's a problem there. Velocity, you will be given rotational speed in revolutions per minute, meaning that to get this velocity, you will say my velocity is equal to pi dn over 60. Pi d n over 60. Now here, all we are doing is use the formula V equals omega r, and then the rest works out like that. So like we've said, mu, that's our coefficient of friction, W is the load, then D is the one we've just talked about. But here, I'll need to emphasize that we're using meters per second as per tradition. That's always our SI unit for velocity, linear velocity, because that's the one we're trying to use. And of course, use rotational speed in revolutions per minute. Now, let me get this clear. We've talked about heat generated inside a bearing. So when heat has been generated, if you don't take care of this heat, it may damage your equipment, it may damage your bearing, it may cause failure. Because it will accumulate, it will start heating up. And then once it heats up, that's where sometimes you even see what will look like fires being formed or overheating taking place until you see some of those members now creating heavy friction. So then we need to remove the heat. So this is where we talk about heat being removed or dissipated by the bearing, heat being conducted away by the bearing, heat being disposed by this bearing. So how do we determine that heat? Now, to determine that one, you will need these conditions. So we say, first of all, QD is equal to C, then A, TB minus TA. Let's start with C itself. This is a coefficient. We call it the heat dispersion coefficient, given in watts per square meter per second. A is the cross-section area, or the projected area of the bearing, of course, in square meters. Then the two temperatures, TB and TA, we have the temperature of the bearing and also the temperature of the air, or the temperature of the environment, the surrounding. So heat dissipated, Ca, TB minus TA. So here we talk about when for unventilated bearings where you're dealing with still air, C is between 140 to 420. That's the average value for that coefficient. If your bearing is well ventilated, then the value for C also goes up. It's between 490 to 1,400. Meaning, for ventilation, we're talking about heat blowing through your bearing, heat being conducted away from your bearing, also with the help of the air around it. So if that is the case, then you'll see that coefficient is between 490 and 1,400. Whichever the case, when these two conditions are given, sometimes, like you'll see in the example, we may use an average value and we proceed, or maybe provide it. All right, so in by experiment, the temperature of the bearing is between the temperature of the oil and the temperature of the air. In fact, this even makes sense because the bearing is sitting between the two. Oil is inside, then the air is outside. So between the two temperatures, that is where you have the temperature of that bearing. So if you have to do that, if you are trying to find the temperature of the bearing, then this is the expression you use. Temperature of the bearing, take out the temperature of the air, is equal to half the temperature of the oil minus the temperature of the air. So from here, if one of them is missing, you can make it the subject and find it. So typical example, I can make temperature of the bearing the subject of the formula, or I want to know the temperature of the oil. As long as the others have been provided, I can come here and get that temperature for use in the other analysis. I'm trying to design a bearing. What is the procedure? Well, first, you need to choose the correct length of the the length to diameter ratio. You refer to some standard tables. So from there, at least you'll be able to know the length of the bearing. Then check on the standard tables. What should be the bearing pressure? And this is where we say the bearing pressure will be given by P load over L times D, where L is the length of the bearing, and D, that's the diameter of that journal bearing. Then W is the load. Then you can select the correct lubricant for the same. Lubricants come in many, you have a huge variety of them. So again, you're going to have suggestions from the tables, which lubricant works for this particular bearing. With the conditions provided, a lot of experiments and work has been done. So you should be able to feel free to select from the tables and then you pick what will work for your mechanism. Then you can select the right operating value factor according to the temperatures you're dealing with. Pick the clearance, the clearance, which is C over D from the tables. Then determine the value of the coefficient of friction. This is something you can easily calculate. Then what about the heat generated in the bearing? We'll soon see how this is supposed to be done because that's one thing you also have to find. Then heat is being generated. Also find the heat that is going to be removed from the bearing, the heat that is going to be dissipated. Then thermoequilibrium, because here you want to be sure that the heat that is going to be generated in the bearing is removed, is taken to the environment. It's not being held in the bearing. So that is where you now pick the correct coolant to do that. Which lubricant are we using? The lubricant is not enough. Find a deliberate coolant that perhaps may even take up the other function. Okay, so now that we've discussed all these factors, let's look at some application. Let's look at some example. So here's my example. We have a load on the journal bearing, which is 200 kilonewtons, to the turbine shaft of diameter 400 millimeters, running at 2,000 revolutions per minute. So what we need to find is the length of the bearing if P the allowable bearing pressure is 2 newtons per square millimeter. Then the quantity of heat to be removed by the lubricant per minute if the temperature of the bearing is 60 degrees Celsius and or viscosity at this temperature is 0.02 kg meter second and bearing clearance 0.02 millimeters. Let's collect information provided. The first thing that you can see here is the load. The load is 150 kilonewtons, 150,000 newtons. So 150 I multiply by 10 power 3. So that's how come I have 150 kilonewtons. I also have the diameter, D. The diameter that I have is 400 millimeters. I want to keep the 2. So what I would do is to convert this 400 millimeters to meters. As per tradition, when you are converting millimeters to meters, multiply by 10 power negative 3 or just divide by 1000. So when you do that, this is the answer, 0.4 meters. Rotational speed has been provided as 2000 revolutions per minute. Our rotational speed is 2000 revolutions per minute. Then we also have the bearing pressure. The bearing pressure is 2 newtons per square millimeter. Already said that the bearing pressure is that critical pressure, or that's the pressure at which we expect this to be operating. Z, that's the viscosity, absolute viscosity of the bearing lubricant. So in this case, it's 0.02 kg per meter second. Clearance. This is where now we push in the lubricant. So it's 0.25 millimeters. You can convert it to meters, but for now, you'll see how we're going to make use of this without trouble. So what do we have? In summary, we have the load on the bearing, which is 150 kilonewtons. All we have done is to convert the kilonewtons to the normal unit, the SI unit, which is newtons. So we've multiplied this by 1,000. So we end up with 150,000 newtons. The diameter is 400 millimeters, so we have 0.4 meters. All we've done is to convert the 400 millimeters to meters. Then the shaft is running at what speed? It's already here. So N, rotational speed, is 2000 revolutions per minute. Then the bearing pressure provided is 2 newtons per square millimeter, which is like 2 megapascals or 2 meganewtons per square meter. But otherwise, we'll keep it in this format for now. Absolute viscosity of the lubricant being used as 0.02 kg per meter second. Clearance in the bearing is 0.02 millimeters. Then we have the constant, K. So this is a standard number. In other words, you check here, check. You find that it's not provided. So this is one standard number that you'll be using, 0.002 for K. Meaning it may not be given. It's one of those standard values you have to keep by heart, just like we always know the value for G is 9.81. It's acceleration due to gravity. So we include this one as well. With this information, let's start with A. So the first thing we can see is that we have the bearing pressure, P. The bearing pressure, P, is supposed to be load over cross-sectional area. So with this, we can make area the subject of the formula. So what are we going to have? The load is, you make area the subject, it's load over the bearing pressure. Now remember, the load was 150,000. The bearing pressure was 2 newtons per square millimeters, and we left it like that. So what do we get? When we divide this, the answer you get is also in square millimeters, because this is in newtons per square millimeter. Next, we're talking about this area, projected area of the bearing. It's supposed to be A is L multiplied by D. But if you check our data, you'll notice that we already have D. The diameter of the bearing, the diameter of the shaft which is rotating was 0.4 meters or 400 millimeters. Here is where you have to be very careful, because this is 75,000 square millimeters. So when I come here, when I'm trying to use this formula, I maintain 75,000 millimeters, meaning that even the value for D should be same millimeters. So as I try to make L the subject to find the answer, it means that the length of the bearing that I'm going to find is also in millimeters. So I have the length of the bearing is 187.5 millimeters. If I had wanted to work in meters, here I should have said times 10 power 6 to ensure that this one is in newtons per square meter. Then here, I'm also going to use 0.4. And the answer I was going to have here would have come from there already in square meters. And my answer was going to be 0.1875 meters. But here we've worked in millimeters, and this is our answer. So all the same, we're still very much on the right track. This is in our final answer. So that's our answer that we have. What about the coefficient of friction? So coefficient of friction, we said it is equal to, this is for our journal bearing, 33 over 10 power 8, then Zn over P, then D over C plus this K. So let's substitute. This is 33 over 10 power 8. Then Z first of all. This is our lubricant, the absolute viscosity. At what speed is it rotating? Is 2,000 revolutions per minute. Then I have the 2, which is the bearing critical pressure. Then the diameter of the bearing, also in millimeters, is 400. Clearance, we didn't also convert. It remained in millimeters. So I have 0.25 millimeters. And we already said the value for K, the standard value for K is 0.002, 0.002. So fight your calculator. When you're fighting your calculator, you can enter this in steps, perhaps to deal with what is on top there. Then you divide what is below there and use the brackets. Then you add the last number. The answer that you should end up with is 0.01256. Now let's get this straight. The coefficient of friction that you should be having here should be very small. If it is rising, approaching 1, then we're having too much friction and it's not good for your bearing. For this, 0.0 something is at least a good number. Then we also have speed, velocity at which this shaft is running. So the formula we use is V is pi dn over 60, pi dn over 60. So then we can substitute. Now, interestingly, here I'm going to use the SI unit for speed, meters per second. So that's why in my substitution, first of all, I have pi. Where there's d, I'm using the meter, so 0.4 meters, multiplied by the 2000, which is revolutions per minute, then divide everything by 60. What do I have after that? When I enter this, my answer is 41.888 meters per second. Now let me check back. Let me just pause and take us back a bit. I have two items here. The first thing I have been given, the first thing I have is coefficient of friction. The coefficient of friction for a journal bearing is 33 over 10 power 8, then Z n over P multiplied by D over C, add K. And then all I did was substitute. My Z is 0.02, rotational speed 2000, bearing critical pressure, or rather bearing pressure is 2, then the D is 400, and clearance is 0.25. Then I add the K, which is 0.002. This is a standard number. So this is how come my answer was 0.01256. What about the velocity? The velocity I have is pi dn over 60. So all I do is pi multiplied by the d, which is 0.4, because it's in meters. Then this is the 2000, referring to the rotational speed. Divide everything by 60, then I have my velocity. Now, you could be wondering, why have we taken, don't we already have our answer? Now, here's the thing. We want to find, we're dealing with heat. So the first thing we need to know is how much heat is being generated in the bearing. So this heat being generated in the bearing is coefficient of friction by the load, by the velocity. So that's why we've taken time to calculate coefficient as well as the velocity. Because the load on the bearing is already there. If it's not there, you should be given clues to find it. Once that has been done, then you can come here and do the substitution. So we substitute our coefficient of friction, 0.01256. Load was 150 kilonewtons, which is 150,000. What about the velocity in meters per second? It's here, 41.888. So heat being generated, therefore, is 78,916.992. That is now in joules per second or watts. So 78,916.992 watts or joules per second. So what do we do with this heat? Well, you can decide to conduct it away. Like we'll see in the next one. We'll talk about heat being dissipated. We'll see how that is done. So here's our question. And this question is saying, we have a journal bearing, the diameter is 100 millimeters, bearing pressure 2.4. The speed of the journal is at 1,500 RPM. Ratio of the journal diameter to the clearance is 1,000 rather. Then the bearing is lubricated with oil whose viscosity at 75 degrees Celsius is 0.011 kg meter per second, kg per meter second. Room temperature, 28 degrees Celsius. This is like the temperature of the air. So determine the amount of artificial cooling required. So here is where we are saying the heat is going to be generated in the bearing. And then the bearing will try to get rid of that heat. Then the question is, how much will remain requiring for perhaps some blower or some mechanism to get rid of it, or maybe some some coolant. So here, what mass of oil is needed if the difference between the outlet and inlet temperature of the oil is 15? So given specific capacity of the oil is that. So we'll come to this and see how this can be done. For now, let's pick up our information provided. The data given starts with the diameter of the journal, which is 100 millimeters, 0.1 meters. We divide this by 1,000 to convert to meters. What is the length of the bearing? Is 200 millimeters, which is like 0.2. Bearing pressure, 2.4 newtons per square millimeter. Rotational speed of the journal is 1,500 RPM. Rotational speed of this member, which is under load, is 1,500 RPM. The ratio between the diameter and the clearance is 1,000. Absolute viscosity of the lubricant, 0.011 kg per meter second. Temperature of the oil, 75 degrees Celsius. Temperature of the air, this is the one which was called the room temperature, This is now like referring to the temperature of the environment. So it's 28 degrees Celsius. Now, we were given the difference in temperature, which will be needed for that lubricant as it is trying to take away the heat. The change in temperature, the difference in temperature is supposed to be 15. So we'll get to this sooner. Now, let me take you back. You will notice, first of all, the specific heat capacity for the oil that we'll be using for removing the heat that will be accruing is 1,900 joules per kg degrees Celsius. And also the value for K, this is one we said you don't even need to struggle. This is a constant, it's a standard number. So you have K is 0.002. Now, also want to emphasize on this item here. How would you know that this is just change in temperature? Because these others are straightforward. I have the temperature of the oil. I have the temperature of the air. I can already see that I don't have the temperature of the bearing. But what is this doing here? How did I find the 15? Let me take you back to the way the question was phrased. Here the question is saying, the bearing is lubricated with oil, whose absolute viscosity at the operating temperature of 75 degrees Celsius may be that. And, oh, sorry, not this one. It came out in here. The mass of the lubricating oil needed if the difference between the outlet inlet temperature, the outlet and inlet temperature of the oil is 15. Can you see the reason we say change in T? Here we are already told that this is the difference between the outlet and inlet temperature of the oil. It's like T2 minus T1, outlet minus inlet. It's here 15. So T2, which is the outlet temperature, minus T1 for the oil that they're going to use for lubricating is 15. Now, when you write like this, the other way of writing what I've just put up here is just to use a symbol where we say change in temperature or temperature gradient or temperature difference. So the change in temperature, that's T2 minus T1, that is our 15 degrees Celsius. So the rest are just provided like that. Then the ratio between the diameter and the clearance, this one that is stated out, absolute viscosity, then temperature of oil and temperature of air. And this is the one I'm talking about. The difference in temperature, change in T. Then specific heat capacity of the oil, 1900 joules per kg degrees Celsius. Constant K, that's 0.002. Let's get to work then. Let's start by finding the coefficient of friction. You will notice that that coefficient of friction wasn't given. So we go back to the same formula. Coefficient of friction is equal to 33 over 10 power 8. Then I have Zn over P. Zn over P, then D over C plus K. Now, you will notice this D over C, the ratio between the diameter of the bearing or the diameter of the journal and the clearance has already been given for us. So we don't have the individual numbers like previously. We already have this. Just like if you have been given the bearing characteristic number, you can substitute the whole of this under one number. But for now, we already have individual values for these. Let's go to the substitution. So this number remains the 3 over 10 power 8. Z, which is the absolute viscosity of the loop, it's 0.011. Speed of the bearing, or speed at which this is running, the shaft is running, is 1,500. Then pressure, the bearing pressure is 2.4. Then we're told that the ratio between the D and C is 1,000. So it's 1,000 over 1, or simply 1,000. So that's how come we replace that with 1,000. You don't need to worry about the 1, because here, when you divide any number by 1, that number remains the same. So if I wanted, or if you want, you can just put 1,000 here. You're okay. Then, of course, these parameters are like that. Don't forget to include the K. Our K is 0.002. So what do I get? My coefficient of friction now is 4.269 by 10 power negative 3. 4.269 times 10 raised to power negative 3. Now, with this now, I'm ready to pick up the next part. So I'll say load on the bearing. What is the load on the bearing? The load on the bearing, if you remember well, we said this pressure, the one we are calling the bearing pressure, is supposed to be load over the area. What is our area? Our area is diameter. It's actually the projected area. Multiply the diameter by the length of the bearing. That gives us the projected area of the bearing. So with that in mind, when you make this load the subject, you just cross multiply. Hence, we're here. So the load on the bearing, therefore, is P multiplied by D multiplied by L. So the pressure is 2.4 newtons per square millimeters. Then the D is 100 millimeters. The length is 200 millimeters. Remember, no mistakes here. We have used newtons per square millimeter. So we are allowed to also ensure that these other two parameters are also in millimeters. D is in millimeters, L is also in millimeters. So 2.4 times 100 times 200. Then we have the load. When you multiply those, 2.4 times 200 times 100, you have 48,000 as your answer. So 48,000 newtons or 48 kilonewtons. But for now, we'll need to use this somewhere else. That's why we'll leave it like that. Oh, sorry. Traditionally, we also need the velocity. Our velocity is pi dn over 60. So pi is pi. D, here is where I keep emphasizing that we want the velocity to be in meters per second. So you cannot use the diameter in millimeters at this point. You use the one which is in meters. So pi times that 100, the diameter. When you convert it to meters, it becomes 0.1 times the n, which is 1,500. Divide everything by 60. So your velocity now is 7.854 meters per second. So you can already see I have velocity as well as coefficient of friction. And the load is here. So don't I already have the full package for getting the heat generated in the bearing? Yes, I do. Because if you remember, we said that heat generated in the bearing, forgive my handwriting there, is supposed to be coefficient multiplied by the load multiplied by that. So meaning I have the full combo, I have the full set, I have the full package that I need for the substitution. So heat generated, therefore, there I am. It's coefficient of friction times the load, again multiplied by the velocity. So with this, now I have heat generated. My coefficient of friction is the one we found to be 4.269 times 10 power negative 3. The load is 48,000. So this is our 48,000. Velocity is the one we've just calculated, and it is 7.854 meters per second. So 7.854. So your calculator, enter this in your calculator. You should be able to find this. And I keep saying that in case you find something different from this, you can always alert me so that I've already seen a number of reactions in the comment section. Others also hitting my inbox to verify where they are seeing small differences here and there. Those are very important. So this is what you get. It's 1,607.53 watts, or basically joules per second. Now, temperature of the bearing, if you remember, when we were writing the data, we had the temperature of the oil, we also had the temperature of the air, but we didn't have the temperature for the bearing. So that's why we go ahead and use this relationship. So we're saying the temperature of the bearing minus the temperature of the air is equal to half temperature of the oil minus temperature of the air. This is the expression we are going to use now, because if you check carefully, we already have the temperature of the oil and the temperature of the air. What is missing is this TB, temperature of the bearing. Temperature of the bearing. So at this point, you can decide to make temperature of the bearing the subject of the formula, and then you just do the substitution. Or you do this, which I believe most of you usually prefer. It's like attempted to make TB the subject of, or a parameter some subject of the formula is like it also gives you extra work. So you prefer to just substitute. But whichever procedure you decide to pick, the results will still be the same. So what we have in our case, what we have here now is this. We are having temperature of the bearing, the targeted culprit there. Take away the temperature of the air. We're given as room temperature, 28 degrees Celsius, is equal to half, in open brackets, 75 minus, this was the temperature of the oil. It was at 75 degrees Celsius. Then the temperature of the air, that's the room temperature. Again, it's the same one we have here, 28. So manipulate the values, try to make TB the subject of the formula. At the end, your temperature for this bearing will therefore be 51.5 degrees Celsius. So temperature of the bearing, 51.5 degrees Celsius. Now, we have a problem. We are dealing with a bearing which is not well ventilated. It's unventilated. Because if it is, the condition would clearly state that. So what are we going to do? We'll pick the average value. We're going to pick the average value. If you notice, the average means that we add 140 and 420. 140 plus 420, and then we pick one value from there. So what are you going to have? You have 560. So what is half of 560? That's where 280 comes in. 280. So this is our average value. Let me go back through that again. We're picking the average value where we're saying, pick this because you say 140. 140 plus 420. So because it's the average, you divide this by 2. So you will notice already, if I add 140 and 420, my answer will be 5, 6, 0. So 560 divided by 2, I'll end up with 2, because 2 into 2 is 2. 2 into 16 is 8, and then 0. So this is where this number is coming from. We're saying it's the average value. We just done the average between these two numbers, and there you are. So you may still have a question at the back of your mind. How would we know if they want us to use the average value? When this, as long as this condition has been provided and ventilated, and a direct number hasn't been given, they've just given us that this is unventilated, then you pick those average values for these two numbers. That's how come. If not, then the value should be given. Then the next thing we find is the projected area. The projected area of the bearing, which is basically L times D. L times D as the formula we've been dealing with. So we have A is LD, so L is 0.1, the D 0.2. And therefore, okay, that gives us the area which would remember there. So our area was 0.02, C 280. Temperature of the bearing is 51.5. Then take away temperature of the air is 28. So how much heat are we going to dissipate? How much heat are we going to conduct away? Is 131.6 joules per second. 131.6 joules per second. In other words, functions of the lubricant, one of them is to lubricate, the other one is to make sure that we conduct away the heat. So here we're trying to establish that lubricant that you are using, how much heat is it taking away? It's this. Now, if this is what it is taking away, the question is this enough to get rid of the heat? Remember, if you check where we are coming from, you'll see that this is what we're generating. This is what is happening inside the bearing. And you just remove 100 and something from this. That's how little the amount of heat that bearing, the lubricant is taking away from the bearing. So meaning the rest of it remains unattended to. So the amount of artificial cooling needed, therefore, is supposed to be the difference between the heat that the bearing is generating and the heat that the lubricant is taking away. So then what do we get from there? We will subtract the heat generated in the bearing. We've already seen it's 1607.53. And the heat that is being taken away, that is being taken away by the lubricant is 131.6. So with this, what do we find? We have 1475.93 joules per second. So with these conditions, we still have this amount of heat that remains, that needs some artificial cooling. Now, heat taken by the oil, heat taken away by the oil. Here, we're already given a condition that suppose we decide to use oil to remove the heat. And then we have the temperature difference when the oil is entering and when it is leaving as 15. So here we'll do this. We want to get rid of that amount of heat being generated in the bearing. So the oil should be able to do that so that we take up both functions, lubricating as well as conducting the heat away, or as well as being a coolant. So what we will do now is mass of the oil times specific heat capacity of the oil times that temperature difference. So how much mass do we need? So we make M the subject of the formula. So we divide through by those numbers. The heat that is being transmitted, the heat that we're trying to remove, the total heat is this 1607.53. Then we have mass M. Specific heat capacity of the oil is 1900. Then temperature difference is 15. So making M the subject, you get the mass as 0.0564 watts. Sorry, kgs per unit time, kgs per second. Now, why I did this is that sometimes the question may decide to ask you, sometimes you may be required to give this answer not in kgs per second, but maybe in kgs per minute or kgs per hour. So in kgs per minute, all you have to do is to multiply the answer by 60. Then you see the value coming to all that. So this is in kgs per second, and that is how much mass we need per unit time, because that's how much flow we're having there. All right, so here's your chance. You can go through the exercise and try these questions for yourself. Yeah. Traditionally, I've already attached the answers, so you can feel free to see where things are working out or where you need clarity.